The world is constantly talking to us. From the music we hear to the vibrations in a bridge, it's all speaking a hidden language of waves and signals. So the question is, how do we decode it? Well, today, we're going to pull back the curtain on one of the most powerful mathematical tools ever invented for doing exactly that, the Fourier transform. So let's rewind a bit, all the way back to 1822, to a mathematician named Joseph Fourier. He made a claim that was frankly revolutionary. He said that any signal, no matter how jagged or complex it looks, could be built by just adding together a bunch of simple, pure sine waves. That one idea, it's the bedrock of pretty much all of modern signal processing.
Okay, so take a look at this. This wiggly line is the waveform of a C major chord being played on a piano. On the surface, it just looks like a complicated mess, right? But what Fourier was saying is that hidden inside this single, complex line are the simple individual notes that make up that chord. The real question is, how on earth do we pull them out?
To find what's hiding in there, we need to completely change how we look at it. We have to make a total shift in our perspective. We need to stop focusing on when the signal wiggles up and down and start asking what it's actually made of. And that brings us to two really different ways of seeing a signal. The first one, the one we're used to, is called the time domain. It's basically that graph we just saw. It shows you the signal's strength or its amplitude from one moment to the next. But our new perspective, this is the frequency domain. It totally ignores the timeline and instead gives us a simple recipe of all the pure frequencies that were mixed together to create our signal. Yeah, think of the frequency domain as a recipe. Instead of one complicated waveform, it just gives you a list of simple ingredients. Those are the pure frequencies. And it tells you exactly how much of each one you need. So for that piano chord, this means it'll show us the distinct notes hiding inside, the C, the E, and the G. So how do we get to this frequency domain? How do we make that jump? Well, we need a special kind of tool, something that can take our complex signal and split it apart into its basic components, kind of like how a glass prism splits white light into a beautiful rainbow of colors. And that tool, that's the Fourier transform. Yep, this transform is the mathematical engine that does all the heavy lifting. It's what lets us make that shift in perspective. You feed it the messy, time-based waveform, and what it spits out is a clean, clear map of all its frequency ingredients. Okay, whoa, I know. That equation looks intense, right? But here's the secret. You absolutely do not need to solve this to understand what it does. The core idea behind all that math is actually surprisingly intuitive. So, conceptually, here's what's going on. The transform is basically a frequency detector. First, it picks a frequency to test for, let's say 100 hertz, then it multiplies our entire signal by a pure 100 hertz wave. Now, if our signal already has a lot of 100 hertz in it, the waves line up and reinforce each other and you get a big result. If not, they mostly cancel out and you get a number close to zero. The transform just does this over and over again for every possible frequency, building a complete map of what's inside. And here it is. This is the payoff. When we run our piano chord through the Fourier transform, bam, the mystery is solved. You see those three big, tall peaks? Those are the fundamental frequencies for the notes C, E, and G. The smaller peaks are the overtones, which is what gives a piano its unique sound. We just turned that messy wave into a simple, readable musical recipe. But this isn't just a cool party trick for music. This mathematical prism, this ability to see the hidden frequencies inside signals, is used to understand and engineer our world in some absolutely mind-blowing ways. Take engineering, for example. Every single machine with rotating parts has a unique frequency signature. So engineers can monitor the vibrations of a jet engine, and by using a Fourier analyzer, they can spot tiny, tiny changes in that signature. A new frequency popping up might mean a ball bearing is about to fail, letting them fix it before a catastrophic breakdown. How cool is that? And you interact with this every single day. I mean, think about the music on your phone. How do we get these gigantic audio files to be so small? Well, the Fourier transform is the key. It lets an MP3 encoder look at all the frequencies in a song and literally just throw away the ones our human ears can't hear anyway. And those noise-canceling headphones? Same trick. They identify the frequency of the annoying background noise and create the exact opposite wave to cancel it out. Its reach goes even deeper, right into fundamental science. Physicists use the transform to solve some of the gnarliest equations that describe how heat flows or how waves move. It's even a cornerstone of quantum mechanics, where it describes this fundamental relationship between where a particle is and where it's going. Now, in the real world, of course, things get a little messy. The the math isn't always perfect on real, noisy signals. So engineers have a trick up their sleeve called a windowing function. You can think of it like choosing the right lens for your camera. A handing window is a great all-around lens for most situations, but a flat-top window is like a specialized macro lens you'd use for getting super precise measurements. It's a crucial step for getting clean, reliable results. But for all of its incredible power, the Fourier transform comes with a catch, a fundamental trade-off that is just baked right into the mathematics and the laws of nature. And that trade-off is the famous uncertainty principle. Here's the deal. You can't have it all. You can know exactly when something happened, or you can know exactly what frequencies were in it, but you can never, ever know both with perfect precision at the same time. The more you zoom in on the timing of an event, the blurrier your frequency picture gets, and vice versa. It's just a fundamental compromise of the universe. So, after all that, what's the big idea here? What is the one thing you should really take away from our look at this mathematical prism? The bottom line is this. The Fourier transform is so much more than a scary-looking equation. It's a whole new way of seeing. It's this powerful lens that reveals the hidden structure, the hidden information that's encoded in all the waves and vibrations that make up our universe, from cosmic signals down to tiny quantum jumps. It's a tool that lets us translate the universe's hidden language into a form that we can actually understand and use. And that really makes you wonder, doesn't it? What other secrets are out there just waiting for us to decode them? What are we going to hear next?